Hi everyone, today we are going to see a topic Faraday's law of induction. And before going to this topic, you have to know what is magnetic flux. Magnetic flux is denoted by phi base for a magnetic field, phi b. Magnetic flux, and if you take a magnetic field lines, say consider this is the area, the magnetic field lines which is passing perpendicular to the surface. Say we have some field lines passing perpendicular to this surface. This is magnetic field. This is magnetic field. Perpendicular, it should be 90 degree with respect to the surface. Okay, if a magnetic field passing through the surface which is perpendicular, that we call it as magnetic flux. Okay, these are magnetic field lines, we know, right? Magnetic field will be having field lines which will pass from north pole to south pole, and those things we know. Okay, and here if say here the phi b, what we can say, how many lines are passing, 1 2 3 4, say we can say this is, okay, your flux, magnetic flux strength, say for example it is 4. Now what we can do is we can increase the strength of the magnetic field. If we are going to increase the strength of the magnetic field, the flux lines will increase. That is, it will come closer. It will be come closer to closer. The magnetic flux line will be very closer to each other. Okay. You see here now. What is in this case? The flux will be here 1 2 3 4 5 6 6 lines are passing through the surface. It has been increased. If you are going to increase the magnetic field, the meaning is the flux line is in, magnetic flux is increased. If you are going to increase the magnetic field lines, the magnetic flux is increased. Yes, in the previous case, for some magnetic field it was 4. Now that same field we are going to increase. If you are going to increase, the number of lines is increased. If number of lines increased, automatically the magnetic flux is increased. Okay, and see here in the same situation, what we can do is, here the initially this is the area. Now if you are going to increase the area, the third, this is third situation. The first situation with minimum line, and second situation with maximum, and third situation, this is the third situation. You're increasing the area. Area means the surface area. The surface area. If I'm going to increase the surface area, see here now, 1 2 3 4 5 6 7 8 9 10. Your magnetic flux again increases. Now the value is 10. Understood? First, the magnetic field is there. What is flux? The field lines passing through the perpendicular area, that is perpendicular surface area, is called as flux. And previously, first case, what 4 lines was passing, and the next case we are increasing the magnetic field. If we are going to increase the magnetic field, the lines will come closer. How much the field is increased, that much your lines will be coming closer. Okay, and many lines, many field lines. So flux is again increased in that case. Again, what we are going to do is we are increasing the area of the conductor. This is conductor. Okay, that will talk later. Okay, this is conductor. If you're going to increase the area, again your flux has been increased. Magnetic flux has been increased. Okay, this is the situation. Now this flux is given by the formula, and we know very well, right? It is proportional to magnetic field. Your flux is again proportional to area, again proportional to area, and this flux is given by a formula B dot E. B is a vector quantity and A also a vector quantity. It is not scalar quantity. A is a vector quantity, B is vector quantity. Here the dot product of two vector quantity will be a scalar quantity. Your flux is scalar quantity and it is a dot product of A dot B. The original formula is, the flux is given by B A cos theta, where theta is angle between your magnetic field and area vector. See here in this case, and here the area vector will be acting perpendicular to the surface. Area vector will be acting perpendicular to the surface, and your magnetic field also in the same direction, and the angle between both will be 0. In this case we can say your flux will be BE. Understood, right? And also depend upon what that angle. Say for example, if you take a area it is perpendicular, it is okay. Now the same field, it is in some angle, it is going like this. Okay, it is going in some angle. If it is going in some angles here, it has two components. Okay, say this is theta angle, and this will be, say this is B. This is B vector, and here we will be having B cos theta rotating towards the angle, and perpendicular to that we will be having B sin theta. Okay, and see here only this B cos theta is responsible for what? Flux. See here this B sin theta is now acting downwards. It doesn't have any effect on the flux. Okay, and so your B cos theta, that angle also consider. This is the actual formula for flux. It is B A cos theta, dot product of B vector and A vector. Understood, clear? And this is about your magnetic flux. Now we will go to Faraday's law of induction. And Faraday's law of induction, the Faraday observed something, some observation he made, and then he proposed a law. You have two laws, Faraday first law and Faraday's second law, and what happens in that observation and how the law has been made, we can see. Okay, and observation. Number one, what he done is, we had some magnetic field, and this magnetic field, it is inwards. Inwards we mark with a cross mark. Okay, this is magnetic field, and here we have placed an conductor which is closed loop. Okay, the conductor closed circuit, we can say closed circuit. This is conductor, this is conducting wire, we can say conducting wire. This is conducting wire. This is field, magnetic field B. It is passing inward. Okay, B. If we put mark like this, it is inward. It represents your field lines acting inwards. Okay. Now what he done is, he have placed an current carrying conductor in that magnetic field which is closed circuit. Now he increased the magnetic field, that is changed. Your B, he changed, and when he was changing, he saw and current was induced. He found a current in this particular coil. Okay, while changing. If not, it was constant. If this was constant, there is no any changes. Once he start changing the magnetic field, what he observed was, here a current is being produced. See, this is I. Current is represented by I. Say it is I. Current has been produced, or else he said a current is induced without direct contact. Right? We don't have direct contact. Current is induced and EMF has been induced. EMF is potential difference. Only if potential difference is there, will be having current, and he said a current is induced in this particular coil when the magnetic field is changed. We can say first case, your B changed, current induced. This is the first condition, the first observation. Second observation what he made is, he made the magnetic field constant. Magnetic field lines, or else magnetic field was constant. Now B is constant. What he done is, here we have radius, right? Some radius will be there, and he increased the area size. He increased the size of the conductor. And while he was doing like that, again he saw some current was induced. Yes, and again the third observation. What he made is, now both were constant. The magnetic field and the area of conductor, both he made constant. Okay, both are constant. You can say B is constant, and also area is constant. What he done is, across this he have rotated the coil. He have rotated the coil, and even though he found and current has been induced. Current has been induced in all the three scenarios. The first scenario was B was changing B, a current was induced, and here B is constant, the area was changing. Again he found a current has been induced, and then he made both your magnetic field and area constant. And what he made is some motion. He have turned the conductor, the spin. Okay, it is rotating, the conductor is rotating now. And again he observed a small current has been induced. The meaning is, here the B is changed, here the area is changed, A is changed, area vector, and here the angle is been changed. Here angle with respect to B and your area vector act perpendicular to the surface. See here, if the area vector act perpendicular to the surface, your B is inward. Now you're going to change. If you're going to rotate, what is the meaning? The area has been changed, the angle theta has been changed. Sorry, theta has been changed. Here theta is changed, angle. We have found in all the condition a current has been induced. All the condition. And simply we can say, see here B is changed, here area is changed, here angle is changed, and we know phi flux is equal to B A cos theta. Yes, this is what? Magnetic flux. And simple words we can say, if flux is changed, a current has been induced. If the coil is closed, that is, the current is flowing in a conductor, and conductor, it is in closed loop or closed circuit. Okay, flux is changed, or else you can say the flux linked with the conductor in the closed loop changes, and current, or we can say EMF, electromotive force. Electromotive force is nothing but a potential difference. If potential difference is induced, meaning as the current will be there. If potential difference is there, the current will be induced. Current is induced. That is the Faraday's first law. This is the observation. We'll see what is Faraday's first law. I'll say. You can write Faraday's first law. So, okay. See here, Faraday's first law. We have two law. What the Faraday's first law says, first law states, whenever there is a change in flux linked with the conductor, there will be an induced EMF produced. If the conductor coil is closed circuit. This is the first law. And you can say in different terms, different ways, the motion, if you have some motion in the conductor, what you can say, if there is any relative motion with your conductor and your field, okay, conductor and your magnetic field, what happens, an EMF is induced. For example, you can say like this, if you have a conductor like this, okay, you connect this conductor with an galvanometer. What is the galvanometer? Galvanometer is a device which is used to measure the current, okay. And if you are going to, we are using an magnet, the magnet will produce magnetic field, we know. And say this is magnetic field lines. If we're going to bring close, that is, we are, say this is kept at rest, we are going to move, okay, not only this as rest, whatever, it can be a rest and this can be moved, and this can be kept as rest, and this magnet can be moved. And what is the meaning is, if I'm going to a relative motion, if I'm going to move any one of the things, what happens is the flux linked with this conductor will change. See here, bringing closer, the flux lines will enter more, and going for far away, the flux lines will be less, okay. And if there is relative motion between the conductor and the magnet, there will be an EMF induced, and current, that is induced current, will be there, okay. And that is Faraday's first law. And we know, and what we know, that is flux change, right? And that is Faraday's second law. And we don't say that flux, it is rate of change of flux. The second law states your EMF induced, E, is directly proportional to the rate of change of flux, that is d phi by dt. Yes, we know, right? EMF is directly proportional to your flux line, and here it is given by not flux line, the rate, in the rate how it is changing, that is the Faraday's second law. It is what? Faraday's second law, okay. And here we can say E is equal to your del phi, the magnitude, if you take magnitude, del phi or d phi, whatever, okay, del t, this we call it as average EMF. And if you take instantaneous EMF, this can be replaced by d phi by dt. Those things are basics, those things are very basics. And this again, if you want to see the direction, it will be negative of d phi by dt, and the direction of induced field will be opposite to the direction of your magnetic field, okay. Those things we will be seeing later in Lenz's law. We will be discussing more, and in depth we will be discussing, okay. And hope it is clear. And also, if you are talking about what is I, the induced EMF value, that is what we can say, I is what? I is voltage by resistor. If the resistor, if you take this is R as resistor, d phi by dt into 1 by R, okay, this will be what? The value of the current induced. This is Faraday's first law, and this is Faraday's second law. Hope it is clear. Thank you.